So this video is on voltaic or galvanic cells, which are basically batteries, right? And so I've got two pictures of batteries at the bottom of the page here. And the battery that you're going to work with doesn't look like your standard batteries, but does have all the exact same components. What batteries essentially do is they take chemicals, and these chemicals have a certain amount of chemical potential energy. And that chemical potential energy gets turned into electricity. Now, every day you use a battery in your phone. Your phone has a battery built into it. I mean, if you need a good example, every day the battery discharges, which means the chemical potential energy in your battery turns that into electricity and your phone works. At some point, the battery dies. At that point, your battery has reached what's called equilibrium. When your battery equals equilibrium, it essentially is at the lowest energy state. There's no more chemical potential of energy left to do work, and there's going to be no current flowing out of the battery. The good thing is nowadays you have rechargeable batteries. So when you take your battery and you plug it in at night, it turns the electricity back into chemical potential energy. Okay? However, galvanic or voltaic cells do one thing. Their one thing they do is they take chemicals and they turn it into electricity. This process is spontaneous. It's very thermodynamically favorable. And that means as long as your battery is not dead, the second you plug it in, electricity is leaving one part of the battery and going to the other part of the battery. Because what a battery also is, it's a redox reaction. And in this redox reaction, you have one part of the battery that's losing electrons, and another part of the battery that's gaining electrons. The part of the battery that's losing electrons is going to be called the anode. Okay, the part that's gaining is going to be called the cathode. So in your standard everyday battery, like this Duracell battery over here, okay, there's always like two leads. When you plug things in, what happens is, right, you have one place that, let's say, is the anode. And I don't know which of these is the anode, so I could look it up if I wanted to, but I didn't bother. And that place is oxidation. What happens is electrons leave this place and go through the device that you're using, whether it's your phone or a controller or whatever else it is, right? And then they come back and go to the cathode, because this is the place where electrons are lost, and this is the place where electrons are gained. And so you can identify the anode and cathode in the site of oxidation reduction by the direction of electron flow, right? If electrons leave through the outie over here and this way and go to the innie over here on the cylindrical battery, right? That tells you that this must be the anode and this must be the cathode. If it was the other way, then it would be the other way. Again, I don't know. I have to Google it, right? I'm not going to bother with that right now. Now, the anode is usually a chunk of metal and the cathode is usually a chunk of metal. They are electrodes, and they are the surfaces on which these chemical reactions occur that are really half reactions, essentially, right? And so if you look at this thing right here that doesn't look like any battery you've ever seen, it has certain components or parts. It has two separate chambers. In one of these chambers, okay, these separate chambers are connected. There's solid pieces of metal in each of the chambers. One of them is the anode, one of them is the cathode. We'll figure that out in a second. And there's a wire connecting them. And the wire has a bunch of arrows above it. And the wires are showing the direction that the electrons are flowing. And so even though this battery looks kind of weird to you, since you see the electrons are going from this piece of metal over here, right, to this piece of metal over here on the right, we know that this must be the anode, and we know this must be the cathode. Because the easy way to remember this, by the way, is anox and red cat. And if you don't get what that means, the anode is the site of oxidation. It's where the electrons are always leaving from. And the cathode is the site of reduction. It's where the electrons are always going. So every voltaic cell or battery is going to have an anode and cathode. Electrons are going to leave the anode. They're going to go to the cathode. Now, this thing in the middle here of the two chambers is called a salt bridge. We're going to talk about that soon, but I'm not going to talk about it right now. I will say that it completes the circuit, and we'll talk about what that means later. Completes circuit. All right? And In the beakers or the glass containers, whatever these are filled with other electrolytes. So these are filled with aqueous solutions, and we'll talk about what those aqueous solutions are in 2 pages. All right, so what do we know so far? A galvanic cell produces electricity from chemical potential energy. The reaction is spontaneous. You can always identify the anode by the direction of electrons being flowing. Okay, electrons always flow away from the anode towards the cathode, and there's a salt bridge that completes the circuit. All right, so this old diagram here, right? This is table J, I think, in your reference tables, okay? And we used it for single replacement reactions. And I'm not really going on a tangent here because we're going to find in these batteries, the type of reaction that's occurring is a single replacement reaction. Now, we have 2 metals here and what I'm going to call a spectator ion, all right? And I'll tell you why it's a spectator. In these redox reactions, what you'll notice is the chlorides keep their oxidation number. They're going to be what they call spectator ions. They're not really involved in the reaction. Now, of these 2 reactions, only one of them is going to occur. So for those who don't remember how this table works, what this says is aluminum is more reactive than zinc. And what that means is that aluminum can kick zinc out of a compound, but zinc can't kick aluminum out of a compound. So you should be able to tell me which of these 2 reactions will occur and which won't. Again, aluminum is more active. It's going to kick zinc out of a compound. So which reaction is not going to occur? Remember, zinc kicks aluminum out. So this reaction right here is not going to occur. And this one over here is going to occur. Now notice what happens, and this is really important because it's going to allow you to identify, based upon this table, where the anode and cathode is, because you can see what's going to get oxidized and what's going to get reduced. In this reaction, which I'm going to rewrite down below, minus the spectator ions, you have Al over here, 0, plus Zn plus 2 arrow, Al plus 3, plus Zn 0. What you can see here is there are 2 half reactions. In one of them, aluminum, the solid element metal, is turning into aluminum ions and is being oxidized. So what we want to recognize is the more active metal will be the site of oxidation. And because of that, it will be the anode. And the less active metal, the zinc, is going from plus 2 to zinc 0. It's being reduced. And so what you're going to see is solid as this reaction proceeds, okay, we're going to see that solid aluminum turns into aluminum ions at the anode. And at the cathode, we're going to see reduction taking place. The zinc ions are going to turn to solid zinc. Now, I'm not putting the electrons in or finishing balancing this thing. Hopefully you know that the common multiple is 6, and you could balance that if you had to. All right, let's look at the next page and look at this thing more carefully. Ready? And there's going to be like 6 questions we're going to ask. All right, here we go. So this is a voltaic cell with the following things. I now have put something into the salt bridge. It's an aqueous solution of sodium fluoride. I put aluminum chloride and zinc chloride in the 2 chambers. I have labeled my anode and my cathode, okay, or in terms of what metal is which. Now, again, recall we found out yesterday on the last page, aluminum is the more active metal. So it's going to be oxidized, and the less active metal is going to be reduced. Right? So the aluminum, the more active metal, oxidized. So we know what's going to happen over here. We know that this is going to happen. The aluminum is going to turn into aluminum ions. And I'm going to ignore the chloride because it's a spectator ion. And I'm going to put the 3 electrons here. That's what's going to happen on this side. And that means that this right here is the anode. What's going to happen over here on the other side, and electrons are going to leave the anode and go in this direction here, because they always leave the anode and go towards the cathode. Now let's talk a little bit about this anode while we're here. Well, what's going to happen to the anode over time? Well, what's going to happen is the solid aluminum that this thing is made of is slowly going to be turning into aluminum ions. So this is another interesting thing. The solid anode always is going to lose mass because aluminum ions are not the same as aluminum atoms. So what's happening is aluminum atoms are turning into the ions. So the anodes will always lose mass. All right? Right? The cathode is different, though. The cathode is the zinc. Now, what happens here? Now, I'm going to write out the reactions. I'm going to start, right? Zinc, arrow, zinc, right? Now, what's happening? Zinc is going to get reduced, right? Because this is obviously, now we know this is the cathode, right? So, if it's going to get reduced, we're going to go from 0 to +2 or +2 to 0. Well, if it's reduction, it's got to go down a number, right? So we got to go from +2 to 0. I'll put the 2 electrons in over here, all right? And think about what's happening now. The zinc ions are turning into zinc atoms. And so what's going to end up happening is on the surface of this electrode, the zinc is turning into solid zinc. And so what happens is the cathode actually gets larger. Now this doesn't always happen, but in these voltaic cells it usually does, because what happens is the metal ion, okay, turns into the metal atom, and the atoms precipitate onto the surface. Cathodes tend to get larger, whereas anodes tend to get smaller. So what I always say is, remember the red cat, reduction takes place at the cathode, gets fat, which means the cathode, the site of reduction, is the place where reduction takes place, and the mass of the cathode is going to tend to increase. So let's talk about the salt bridge finally, because we haven't gotten to that, and then we'll balance the final equation. So here's the thing about a circuit. Okay, we don't talk about this much in chemistry because it's more of a physics thing, but a circuit is basically a circle. That's where it gets the name circuit, right? Negative electrons can't just go over here, because if that happens, then negative charges will build up on the the cathode, and get repelled, and the battery would die. If you take the salt bridge out, if you remove it, the voltage goes to 0. It's like your battery's dead. What has to happen here, okay, is that charge has to be able to move in a circular pattern. And so what ends up happening here is particles move in this way, but there's no electrons here. These are all electrolytes. And what happens is ions will migrate within the salt bridge. And by doing that, they will complete the circuit. And so there's no break. And that's always the case. That's how switches work. When you turn off the lights, you're opening the circuit. You're creating a little gap in the circuit. If you break the circuit, then everything stops flowing, right? Now you should know the direction the ions migrate, and it's not hard to do, because the name of the anode and cathode come from what goes there, right? So what goes to the anode? Guess what? Anions go to the anode. It's not supposed to be difficult. What goes to the cathode? Cations. So in our salt bridge, which we have sodium, which is a cation, and fluoride, which is an anion, we know what direction the ions are going to migrate. The negative charge particles are going to complete the circuit and keep going the same, to make the negative charge go in the circuit clockwise, right? So the fluorides are going to go towards the anode in the salt bridge. They're going to migrate. They're ions, not electrons in there. There's no electrons in that part of the thing. The cations are going to go to the cathode, so the Na pluses are going to go this way. Now, I'm now going to write out the overall reaction and label it, and then I'm going to do another one where I just give you the answer, okay? And you try to figure it out for yourself. Here we go. The last thing I want to do is talk about this. You have 3 electrons here and 2 electrons here, and you know how to balance it. You're going to multiply the aluminum reaction by 2 and the zinc reaction by 3. So your balance reaction is Al with a 2 in front of it plus Zn2 plus with a 3 in front of it, arrow Al plus 3 with a 2 in front of it, plus 3Zn0. That's your balanced redox reaction. Now notice, this is solid. This is solid. This will always be the anode. This other solid will always be the cathode over here. It's alphabetical. You can't forget it. All right? Notice what's happening. The zinc ions are turning into zinc atoms. So the cathode is always going to increase in mass. The red cat's going to get fat because these zinc ions are turning into zinc atoms and they're sticking to the cathode. The anode is turning into ions, which means the anode is always going to get smaller. All right? Because this reaction only proceeds one way, unless, of course, you recharge your battery, in which case you reverse the reaction. And that's how And in that case, everything I just said will be backwards. All right, so let's so quick summary before I show you the last thing, because we're going to run out of time. Quick summary: oxidation of the anode, it's the more active metal. Reduction of the cathode, less active. Electrons will flow through from anode to cathode. Right? Within the salt bridge, ions will migrate. The anions will migrate to the anode, the cations to the cathode. In the balance reaction, the anode will always be the solid on the left, and the cathode will be the solid on the right. Electrons will always. The anode will always decrease in mass, and the cathode will always increase in mass. So I'm maxed at 15 minutes, so I've got the setup here. I'm going to put up the answers. I'm going to put the balanced equation. I'm going to put up the direction of electron flow, the direction of ion flow, and everything. You should try to do it yourself. So these are all the answers I can't spend time explaining because I'm running out of time.